Okay, this is a pretty typical problem that we encounter when we work with vector data, and we have kind of a zonal question. We want to know, for instance, maybe what is the population of this voting district W, given that we only really know the current population by census tract, which is a completely different shape. So using that example, let's pretend these are census tracts that represent the same area, and these are their voting districts. In the voting districts, we don't know the population. We only have an ID for which precinct or something they report to. So we need to make an estimation. Well, what we want to do is we want to do an areal weighted reaggregation, which is kind of a mouthful, but really what it means is, for instance, this 100, this set of people here, 100, how many of these 100 people should go to voting district W versus voting district X? Well, hopefully you might say, okay, probably 50 apiece, right? In a very simple kind of model, we would say half go to W and half go to X, because this boundary of the district would split this census tract in half. So that's all there is to it, really. We're using area, 1/2 of the area. That ratio, 0.5 times 100 equals 50. 50 goes to each. Now, there are some issues with that, one of which being we're assuming that there are 100 people that are homogeneously spread across this one zone. And, of course, we know that there are different densities of housing developments. There's mixed use, commercial, residential kind of zoning areas. We can't really get into that at this moment. You might also look at the modified aerial unit problem or kind of asymmetric mapping techniques. There are ways to deal with that problem. For instance, you might erase industrial zones or places or water or places that people actually don't reside. But for a basic vector operation in which we're trying to just estimate as best we can how many of these people go into the new zones, we're going to use areal weighted reaggregation. And this is a very simple example that's nice and clean. So that's all we can do for now. Okay, so the first thing we have to do in order to make that ratio is we have to calculate the area, kind of area 1. What is the area of these origin geographies? So calculate area 1, very good. And we're going to use this kind of destination file twice. We want these values to end up here, but we have to kind of intersect them first to break it into pieces so that we can kind of estimate how many people are in each piece before we smush them back together. So I intersect the origin and destination geographies, and voila, I get kind of a very complex set of, it's really just the product of these two tables is what we're seeing down here, every possible combination when they spatially, when they intersect. So originally in our attribute table, we just had an ID, a population, and area 1. Now we have a new ID for each new shape, and we have the ID of the origin shapefile and the ID of the destination shapefile, and the population and area 1. So we get kind of these redundancies, right? 100 shows up twice, 10 shows up twice, etc., etc. What is important to note here is that there is a parentage to each new polygon, kind of each new shapefile geography. So what we're going to try to do is take those values, and then when we weight them with area, we'll come up with an estimation of how many of those, for instance, 20 people should we put into 4. And hopefully we're going to say 10 should go into 4 and 10 should go into 5. Because 4 represents a piece of Y and 5 represents a piece of Z, the destination geographies. So I'm going to estimate a population for the intersected geography. Oh, sorry, I'm going to calculate area 2 because I have to get area 2 so I can divide it by area 1 to get my ratio, right? Calculate area 2. In our case, it's all perfectly half. So now that I have area 2, right, 5, I have area 1, I can say area 2 divided by area 1 is going to be 0.5 in this case everywhere. Multiply it by the original kind of population, and then I get my best estimation of the population in each intersected geography. In this case, here we go. Now we can kind of see, okay, yep, 25, 25, 10, 10, 5, 5, 50, 50. So that's great. What we've got is our kind of estimated population for the intersected geographies, kind of given this intersection and given the original source data. So now we've got to reaggregate. Boom. Great. So we kind of know our best guess of how many of the raw count, in this case population, is in each small piece. But what we really want to know is how many, again, are in W or X or Y or Z, those kind of destination geographies. So we kind of have to dissolve, for instance, this middle boundary here. So instead of 50 and 25, we have 75. Instead of 50 and 5, we have 55, and 15 on the bottom and 35 on the side. So we're going to use a tool called dissolve, which takes a field and will get rid of kind of duplicates. It'll take WW and combine that into just one W here. But what we really want to know is when you combine these two or kind of collapse them, what do we do with our weighted population values? Well, we want to sum them. So you have all these statistical options when you dissolve. How do you want the program to report this this statistic here? And you say, okay, I want you to sum. I'm going to dissolve by the destination ID. So you might have noticed that the one error I have in my diagram here is that I say dissolve by the origin IDs. This word origin should read destination. I've lost the original project file. I apologize for that. Just, in your brain, try to forgive me and switch the word origin to destination. So I'm going to dissolve by the destination IDs. I don't know if you saw that. I'll do it again. And when you dissolve and you make sure to say, I want to sum the weighted population, you should end up with these values in the end, which, given our original data and our method, is the best way we have to kind of make a zonal assumption or estimation. So go ahead and look through that again. Most of these operations happen in the field calculator, right? Calculate area. It's a geometry problem, both in QGIS and in ArcGIS. Intersect, this is a geoprocessing command. You're actually going to be taking one file, two file, making a third file. I usually call mine intersect or something like that. After you do that, you're going to be working with your intersected file, and you're going to calculate an area again. This is a field calculator or a geometry, calculate geometry issue, meaning your area needs, your shapefile areas need to be projected. Can't do this on unprojected data. The next one, of course, is a field calculator problem. You're going to be using these fields to estimate and create a new field, weighted pop. So far we have field calculator. We've only done one geoprocessing command. With the dissolve, that's our second geoprocessing command. I say manage your table as a step. All I mean to say here is that sometimes it's kind of confusing. You've got this big array, this large table, this large attribute table, and you want to make sure you know what you're going to dissolve on, which should be your destination ID, not origin, destination ID, and how do you want to report anything else that exists. You will want to sum the weighted population in this case, but you may have a name, or maybe you're bringing through other fields that you want to do other things to. But manage your table, know what things mean, and then go ahead and dissolve by destination ID, and you should end up with what you're looking for. So hope that's useful. If it is, or if it's not, leave a comment. Someday perhaps I'll open up the Flash file and rehash it out again. But for now, better use on the web than just sitting on my laptop. So good luck.